Today we face our final curtain. So we haven't been able to go through a lot of the material paradoxically, but let's do our best to cover what remains. So you all received the exam, correct? Well, I hope you find the questions not to be too difficult. And you saw the first question, yes? Make sure you truly solve it, and take it to heart. Because last exam you did not. Not all of you, for sure. All right, so X is distributed over the interval AB uniformly if the density function is given as a constant. Now, this is very natural, guys. So what is this uniform distribution supposed to describe? It's that every outcome within the range of X is equally likely. Does it make sense? If we make X a discrete random variable, then each region is equally likely to be an outcome. Do you agree? So if we imagine building the histogram towers that are very thin, if we're dealing with a uniform distribution, those histogram towers will be of exactly the same shape, exactly same height, like much of Soviet architecture, uniform. So what should be, if it's spread over the interval from A to B, the constant C has to be 1 over B minus A because the full area has to equal to 1. You agree? So the integral C times B minus A, should be 1, and that makes C equal to 1 over B minus A. Now, the cumulative distribution where X is less than T is just the integral from minus infinity to T from A to T, which is then simply T minus A over B minus A, and its shape is like this. You can see that below A, obviously it's 0. As I move towards B, we have growth in a straight line until we reach 1, and then it becomes 1 forever. So another very useful thing to note, guys, is that if X is uniform random variable over the interval AB, then the probability that X is in A is simply the length of that interval I divided by the length of the interval, the overall interval in which X takes place. So it's the length divided by B minus A. So here is a simple example. Suppose that X is uniformly distributed between 0 and 20. I would like you to tell me what's the probability that X will assume a number between 5 and 10. Go ahead, calculate and write in my message. I hope you understood that you don't really need to integrate, correct? You don't, it's immediate. What's the answer? Why is there no answers? One over 4. Thank you, Sarah. The answer is obviously 1 over 4 because this interval is of length 5 units and it makes 1/4 of the full length. In other words, 5 divided by 20 is 1/4. And similarly, this interval here is of length 3/4. Good? Guys, before I continue, any questions? Do you understand that the uniform random variable is the analog of equally likely outcomes that we did in the discrete case. So here is another example. Suppose theta is uniformly distributed over the interval from 0 to 2 pi. Compute the probability that sine of theta is less than 1/2. So I decided to calculate probability that sine of theta is bigger than 1/2 or equal to it. And that only happens when theta is between, so over this interval, so when theta is between pi over 6 and pi minus pi over 6. And so this is 5 pi over 6. So sine of theta is bigger than or equal to 1/2 when we have theta between pi over 6 and 5 pi over 6. And this gives us a probability of 1/3. Yes, I think, is there not another interval? So yeah, so between 0 and 2 pi, sine is only positive in first and second quadrant, yes? So, so what you have to then remove is that piece that we calculated. In other words, you remove 1/3. So 1 minus 1/3 gives us the probability that sine of theta is less than 1/2. Here is yet another example. Trains run every 10 minutes. So that means from 2 to 20 to 10 to 20, etc. If you arrive at the station at a time distributed uniformly between 2:05 and 2:35, what's the probability you have to wait under 5 minutes, guys? What's the probability you wait under 5 minutes? Can you calculate it quickly? You arrive uniformly between 2:05 and 2:35. So Ben says 1/2. Thank you. What about the rest of you guys? All right, so let's look at the situation, guys. So you have to arrive between 2:05 and 2:10. So basically 5 minutes before 10, 5 minutes before 20, yes, 5 minutes before 30. That's all. Those are the only possibilities. Yes. So there are 3 possibilities, 3 intervals that are of the same length. The length of each interval is 5 minutes. Yes. So it's 15 minutes altogether that you have available. And 15 minutes divided by 30 is 1/2. Agreed? Here it is, guys. So, I mean, I said x is distributed between 0 and 30, where x plus 5 is between 5 and 10. X plus 5 is the random variable that, that I arrive between 2:05 and what's the other, and 2:35, yeah? So we need, so x plus 5 can be equal anywhere between 5 and 35. So x is anywhere between 0 and 30. And so you can solve and you can see that the probability is indeed 1/2 by comparing intervals. Let's look at Bertrand's paradox. So here we have a chord that is randomly drawn in a circle of radius r. What is the probability that this chord is shorter than the length of a side of an inscribed equilateral triangle? Do you understand? So what the question is, guys? So there you can imagine a circle, and randomly you draw a line that cuts the circle in 2 points. That would be a chord. What's the probability that this chord will be shorter than the length of a side of an inscribed equilateral triangle? That is a triangle that has all sides identical. Two-thirds. Well, that. So I said Nora says 1/2, or maybe it's from the previous question, right? I think only 2/3. I had one solution. Well, guys, first let's try to understand what is an equilateral triangle. So here is the diameter, and I can construct an equilateral triangle. If it's equilateral triangle, then all the angles here are the same. They are 2 pi over 3. Do you agree? And this is the radius of the circle. So what's this length? This length is simply double sine of pi over 3. Right? Sine of, times r, of course. I mean, but if you make r equal to 1, it's just double sine of pi over 3. Do you agree? That's the length of the side of an equilateral triangle. So what is that side? Sine of pi over 3. Sine of pi over 3 is simply root 3 over 2. But what you can do is, guys, you can imagine, first of all, how is the chord drawn? Anywhere where the chord is drawn, I can orient the triangle to be parallel to the chord. You agree? I can just move the triangle so it's parallel to the chord. And if you look at this question, it's as if you can think of it in 2 ways. One way is that we can assume that that the chord is always perpendicular to the y-axis, and every possible chord at any y is uniformly distributed. So any y can be given. You follow? Any y can be given. In that case, what should be the situation? If any y can be given, y is distributed from 0 to r. And y has to be bigger than cosine of pi over 3, or y has to be bigger than 1/2. So then the answer would be 1/2 if you do it this way. You follow how I argued for 1/2, guys, or am I not very comprehensible today? You look like you are dead and I am about to faint. So please let me know. There is barely anything going into my brain. My eyes are getting dark.
Arkady, can you explain that again?
Yes, it's because of not sleeping. I'm joking. So, so yeah, okay, guys. You see what's happening. So you have to imagine it a bit, right? So how are we drawing the chord? So the chord, you can imagine when it's drawn, I can always kind of rotate the circle so that the y-axis is perpendicular to the chord. Can you imagine that? So any chord drawn can, without loss of generality, be imagined as perpendicular to the y-axis. Yes? So then if I understand that the chord is randomly drawn to mean that the chord is uniformly distributed over the y-axis, over the positive y-axis, so I might as well imagine that the circle is of radius 1. I mean, I can just normalize it, right? So this length here is length 1. Now here I have the equilateral triangle. So if it's equilateral triangle, all the interior angles must be the same. So this interior angle that I drew over here must be 2 pi over 3, because I must divide the full circle into 3 sectors, right? Identical sectors. So that's how I describe the equilateral triangle. Guys, are you with me? Do you follow? So so then what's the what is the, when the chord is shorter than this side, it must be within the region from here to here. I mean, from this point to this point is the y-axis, is the y values that are acceptable. Yes. Now for those y values, what must be true is that y must be bigger than cosine of pi over 3, because this region, you can see this is 2 pi over 3, half of it is pi over 3. And this point here will then be cosine. I mean, this length here. This length here is cosine of pi over 3. Agreed? Now cosine of pi over 3 is 1/2. So we only have this region available. And this region is its relative length is 1/2. So the probability that the chord is going to be shorter than this than the side of the triangle is by this argument, it's 1/2. Did you understand this argument, guys? Yes, I just measured the chord and then I assume that the chord is uniformly distributed over the positive segment of the y-axis, which if I want to, I can normalize. Normalize means I can scale it and make it 1. Right, so in other words, the chord is intersecting the y-axis anywhere from y equal to 0 all the way to y equal 1. Yeah, I see all of you are with me. That's fine. I feel the same way, so there's nothing to feel embarrassed, right? Maybe I'll play you a good lullaby. Yes, guys, are you holding? Yes, the cosine part, pi over 3. So do you see the 2 pi over 3 part? Do you see where I get 2 pi over 3? Yes, confirm that you see the 2 pi over 3. Because to make equilateral triangle, I must cut the circle into 3 parts. The full circle contains 2 pi angles, so 2 pi over 3 is the angle between the two inner legs of this equilateral triangle. Now, I want to, you see, why do I take 2 pi over 3? I take half of that angle. Why half? Because I'm interested, you see where I move the cursor, this length, I want to know what part of the y-axis is this? How far on the y-axis does it go? And this length goes all the way to 1/2, y equal to 1/2. Do you see that? Why? Because cosine of pi over 3, cosine of half of this angle, cosine of this angle will be 1/2, half of this length. Yes. So then I labeled the sides as r, but you can rescale it. You can assume r is equal to 1. Yes. And so the probability that the chord is shorter than the side of the equilateral triangle is, you see, the probability this is shorter is the probability it's in the upper part. So from 1/2 to 1. If it's a unit circle, from 1/2 to 1. And if it's uniformly distributed all over this positive y, the probability that it will be in the upper part is 1/2. Yes? But what Sarah said is not wrong either, because the question is, what is uniformly distributed? I can describe the chord as being uniformly distributed on the y-axis, or perhaps the angle of the chord is uniformly distributed. You see, by that I mean perhaps You see this drawing here that I have with the red dotted lines? This is the angle theta. So perhaps theta is uniformly distributed. So this chord is exactly the diameter when theta equals to pi. And it's a tangent when theta equals to 0. So you see theta is like this, right? This angle. If the angle is uniformly distributed, we get an entirely different solution. You see? So if the angle is uniformly distributed, what we get is that this angle is 2 pi over 3, and the angle has to be smaller than 2 pi over 3. So that makes the probability 1/3. I mean 2/3, sorry, right? Because so the angle has to be 2 pi over 3 all the way to 0. And that's 2/3 of pi. The full angle is pi. So 2 pi over 3 is 2/3 of pi. 2/3 pi divided by pi is 2/3. So that would be Sarah's probability 2/3. So you see, depending on what you mean by random, you have entirely different possibilities. The answer could be 1/2 and could be 1/3. And just like with any question that I ask on my exam, it can be very vague, right? No matter how precise you make it, it can be vague. You see here, I go through the explanation again, guys, right? So make sure to look through it. Yes, by the way, does it surprise you? It should not surprise you too much, because think about it, guys. Uniform angle should not correspond to uniform y, right? Because the wider the, you see, how can I say that? You see, what's the relationship between y and angle? Is that the relationship between this theta and y? It's roughly a cosine of half of that angle, right? The relationship is actually cosine of that angle. So just because theta is distributed randomly, it doesn't mean cosine of theta will be distributed randomly. It's a function. Yes. And similarly, if I distribute y randomly, that will not make theta distribute randomly, because that would be cosine inverse of y. All right, that's the relationship. So I mean, I'm not sure if it surprises you, but it should not surprise you all too much. All right, so here is just a basic calculation of the expected value and variance. So the expected value, guys, you just multiply it by x. Integration is very simple, and naturally you would have expected that it's the average. You agree, guys? Even without doing this calculation, you might have known the answer is the average between a and b. So if it's equally likely to be everywhere, it will be balanced around the center. So the expected value of a uniform variable is the average of the endpoints. Good. The expected value of x squared, just calculate it, and you see that variance, just x squared minus the square of this number, it just ends up being b minus a squared over 12. Now there is something that is quite useful, and that's called universality of the uniform random variable. So you see, we study all sorts of continuous distributions, but in fact, if you can generate a uniform random variable, you can generate or simulate any other distribution, and vice versa. And I will show that at least in the case where, the random variable x has a cumulative distribution that is strictly increasing over its definition. Okay, so this is the theorem that we have, guys. So first part of it is, let x be continuous random variable with probability density function fx and cumulative distribution capital Fx. Then x, which is the inverse image of u, where u is uniform over 0, 1. That's the relationship. In other words, what part I is saying is that if I can simulate uniform distribution, I will be able to simulate any such x. You understand? So how is that going to work? So for I, let's look at the proof, guys. So suppose that the function f of x from r to 0, 1 is an increasing function, right? So I mean, it could be a non-decreasing function, but for this proof, for the inverse to work, let's assume it's just strictly increasing. That's the we make it under this assumption, this proof. So then what do we see? So let's take this distribution of x, suppose a distribution of x, and then we can take because the cumulative distribution of x is from r to 0, 1. Then then I can take the inverse image of u, where u is a variable from 0, 1. That makes sense. It will map it into r. Yes. So it's a well-defined function, and I can call y this variable. Now, what's the probability that y is less than or equal to a? That's the same as the cumulative distribution of y, and this is the same as so that's the same. The density function of y is the derivative of this function, which is the derivative of the inverse of u less than or equal to a, which is the same if I apply f of x to both sides, derivative of u being less than or equal to capital Fx at a, which is the derivative of this function. Do you agree? Make sure, guys, that I haven't lost you entirely. Are you able to follow me? Or did I lose you? Well, you see, so first of all, do you see the goal of this theorem? The goal is just to show that, first part is to show that if I have the uniform random variable available, I can use it to create any other distribution, any other continuous distribution. So here, I prove that this theorem is true for the distributions for which the cumulative distribution is increasing, right? So if x is a random variable whose distribution is increasing, then the cumulative distribution has an inverse. And what do we see? We see that the cumulative distribution is from real numbers to 0, 1, and therefore I can take the inverse image, right? So u is from 0, 1 to 0, 1. So I can take inverse image of variable u, and so we have this integral, and the derivative of that integral is little fx. So which means that this y has the cumulative distribution of little fx, and that means that x and y have identical probability density functions. So then we have the second part of the theorem. We can similarly generate the uniform distribution if we have any other continuous distribution. You see, if I have any other distribution, I'm also capable of creating the uniform. Okay, so if I have one, basically what this is supposed to say is that if I have one continuous random variable, I am capable of creating any other. So how would that work? Well, we can set u to be equal to the cumulative distribution applied to x. Okay, so in other words, I just apply the function. Now, why is that useful? Well, we'll look at it. If u is less than a, that's just the cumulative distribution of u, and its derivative will be the density function of u. Now, I want to show that the density function of u is 1. Now, what's the derivative of this expression? It's the derivative of fx of x less than or equal to a, which is the derivative of x less than the inverse function. And if you remember the derivative of this, this is just the cumulative derivative of the cumulative distribution of the inverse. And that means the derivative, they cancel each other out, so that's just the derivative of a, which is 1. So that shows that U is uniformly distributed. Any questions? So here we can talk a little about the normal distribution. So a continuous random variable is said to have a normal distribution if this is the density function. Okay, this is standard normal distribution, to be precise. So it's 1 over root 2 pi e to the minus z squared over 2, where z is capable of taking any real number. Now, to see why that works, guys, with why is that 1 over root 2 pi here? It's because the integral from minus infinity to infinity of e to the minus z squared over 2, that integral must equal to root of 2 pi. And we can see that by first labeling I as the integral from minus infinity to infinity of this function. And then we can see that I can make I have either expressed in terms of x or in terms of y. This is just a dummy variable. Both x and y are dummy variables. And then I squared is the product of both, which becomes the integral from minus infinity to infinity, the integral from minus infinity to infinity of e to the minus x squared plus y squared over 2. Guys, do you remember Calc 3? This is, well, exactly, right? So you aren't you glad that we didn't get to chapter 6 where it is all about Calc 3? It's too bad, right, guys? We have missed, you cannot imagine, I just feel so terrible. We have missed so many remarkable things. You see, the most interesting things, moment generating function, just Jack, look at Jack is just, they cannot bear it, right? Jack is so upset. Me too. So how do you solve this integral, guys? So do you recognize what this integral is, guys? Well, I mean, I have notes on Calc 3 for that. And I consider this, well, I mean, I always think about baking cakes. You know, like you have a sheet of metal, or I call it a frying pan. And I imagine how a cake is made in a frying pan. I imagine because I personally never make cakes. So what happens here, guys, what's the frying pan here? You can imagine the frying pan is the entire two-dimensional plane, which can be described as an expanding circle. And an expanding circle will be one or an infinite circle. I can describe it in terms of angle and radius. So in terms of angle and radius, it is 0 times 2 pi is the integral of the angle, and 0 to infinity is the integral for the radius. And the radius here, we have x squared plus y squared. It's the radius squared divided by 2. And we need to insert the corrective factor r d theta. Do you remember the change of variables, guys, that you need to carry? How many of you remember that, guys? Just by voting, right? In the comments, yes, I remember it, and everything I'm mentioning is old news. Or you don't remember any of it? All right. None of it, right? You don't remember double integrals. Do you remember double integrals? Yeah? here is the idea of double integrals, guys. I'm not sure what's the point of it, but we might as well. Okay. Well, here it is, guys. Right. So this is just let's say it's from 0 to A and from 0 to on the y-axis to B or something like this. Yes. So this is a nicely baked cake. Now it's a brick cake. Do you agree? It's a brick cake, and what you wonder is, well, how many calories are you gonna get when you eat that cake? Yes. Now, if the cake is made of uniform material, that corresponds directly to the volume of the cake. You agree? So what's true about this cake? So you can see that in this case, it's baked in a rectangular baking pan. Do you agree? It's a rectangular baking pan. And the shape of the cake is essentially like a rectangle, except for the crust, right? So the crust has this property. This is crust. It's f of x, y, and that's the z altitude, right? That's the only thing that's not immediately obvious about this cake, yes? Now, how can you measure the volume of that cake, right? So what you can do is you can take several slices, right? So here is, you can take slices perpendicular to the x-axis, so you can cut the cake like this. Right, and this region that you obtain, you multiply by the thickness. And if this is very short distance, then essentially this curve is repeating. So the outline of this curve is, so this area, the slice that I cut out, is the integral for this particular x for y from 0 to b of the function f x y dy dx. Do you agree? Do you see where dx dy came around? Yes? Are you with me, guys? Do you see what I did? We know how to calculate areas, right? So I have this loaf that I sliced out, and f of x y dy represents what, right? The integral from 0 to b f of x y dy represents the volume, represents the area or underneath this curve. You see the curve that I'm tracing here? Underneath this curve, I then can understand the area. And then I multiply it by dx to give this area some thickness, and that becomes volume, right? So if the dx is very small, now I have volume. Do you agree? Are you with me? I'm just reminding you guys, I'm trying to be, as they say, blitzschnell, to remind you what is double integration. Yes, it makes sense? And then, of course, guys, what we need to add over all the dx. So different dx will have a different value for x. So what we do then, if we slice it, then we integrate the dx's from 0 to a. We integrated dx from 0 to a. Do you agree? Now I could have sliced the cake a different way. I could have done the same thing, and I could have sliced the cake this way, perpendicular to the y-axis. Yes, and then here is that second piece. You see? Yes. Now this is dy. This thickness is dy, and then the integral would be what? It would be the integral from so that's the integral from 0. You see, it's perpendicular. It's parallel to the x-axis from 0 to a fx y dx times dy. Times dy. You agree? Y times, so guys, do you see y times dy? Integral from 0 to a for that particular fixed y will give us the cross-sectional area, the surface of the bread. You've seen how bread or cakes are sliced, correct? You've seen the slicing machine. And imagine that the knives of the slicing machine are very close together when you slice your bread. Go to Russian stores, you see that all the time, right? Bread is sliced very thin. And what you have is the surface of the loaf looks like what? The surface of the loaf looks something like this. Yes? That's the surface of the loaf if I cut it along the y-axis, and then this is the length here is from, this is for a specific value of x, so for a specific value of x, and it extends over the y-axis from 0 to b, for instance, right? That's and if you have for a different value of x, it will be a different shaped loaf. And so all I need to do to find the volume of that bread slice is just multiply the area by the thickness, right? Regardless of how I slice. So integral from 0 to a f of x dx is the surface area if I cut it parallel to the x-axis. Times dy, it's multiplied by the thickness. Do you agree? And then I add up over all the slices. To add up over all the slices, that's what you do with the summation. So that's where you have the integral from 0 to b. So basically those two things should be equal. So that's your double integrals, right? Double integrals is just what? It's just you slice it, right? And then each slice has an integral area. And then you add all those integral areas up. That's how you get double integral. You agree? Now the shape can be, I might describe that a bit later. It doesn't have to be rectangular, right? It doesn't, maybe this is the rectangular frying pan, right? So in essence, you can actually, when you consider the integral, you just have to focus on the frying pan. The function is already available for you. It's the f of xy that you're integrating, yes? Could you describe, guys, I want you to describe bounds of integration if you understand how that's done for maybe this triangle. Imagine that I have this frying pan. So this point, this is a view from above. So the z-axis is coming at you here. That would be the z-axis. That's a view from above of your baking pan. It's a triangular baking pan, and here we have coordinate is 1 here. The coordinate is here is also 1, and this is a straight line. So this obviously is a line. So I would like you to describe the cake is above, right? The cake is hovering over it. I'd like you to describe. So maybe the cake is given by x, y, something like this. That's f of x, y. I would like you to set up this integral, please. Set the volume of this cake in terms of slices first that are perpendicular to the x-axis. So I want you to describe the volume of this cake in terms of slices that are perpendicular to the x-axis. Can you do this? You see what happens here? Yes, guys. So if you select a different x, you have a different length slice. So you need to describe for an arbitrary x, what's the length of the slice? What am I doing with it? So this is the function, yes, guys? It could be anything else, doesn't matter. In general, it's f of xy. I just made it simple for us, okay? So let's look at it together. What is this point? If this is xy, what is this point, guys? So I need to look at this expression. This expression is a line, and it's a line that that has a negative slope and goes through the point 1, right? So this line, you can actually verify it's x plus y equal to 1. Do you agree? If x is 0, y is 1. If y is 0, x is 1. Which means that with respect to y, I can write it as y equal 1 minus x. Which means that the area of the loaf of bread, you see, if I look at this loaf of bread, the area is for that x from 0 to 1 minus x fxy dy. That's the area corresponding to the loaf at position x. Guys, you all understand what I'm saying, area of the loaf, position x. So I did not draw the loaf, right? This is the view from the top. Now imagine you cut the bread, and the bread was baked in this triangular baking pan. At position x, there is a surface area to the slice. Do you agree? And the area of that slice is given by this expression, integral from 0 to 1 minus x f of xy. Agreed? And then all I need to do is to find the volume. The volume of the full loaf is given by x has to change from, we need to sum over all x from 0 to 1. And then we have this. Agreed? Guys, are you remembering now? You see what happens? Can you imagine? It's I'm hoping that the probability trained you somewhat, right? I mean, the probability is much harder than this, right? We have to imagine much more vivid things than just slicing bread. Yes, f of xy is xy. I'm not interested in solving it. I could, but what's the point, right? So that's the slice here. Could you maybe help me with one more example, guys? So we have now the frying pan is now like this. So this is not like this. Sorry. It's now like this. I mean, like this. Where this is 0, this is 1, and this here on the y-axis, this region corresponds to 2. Okay? I want you to tell me, I want you to do two things, guys. I want you to set this integral in two ways. You see? It's a line. I want you to tell me using vertical slices, what's the setup for this integral, and what's the setup for this integral using horizontal slices. Again, viewed from above. So when I mean vertical and horizontal, you understand based on this drawing. And the function is just some f of x, y, doesn't matter what it is. If you want to, it can be e to the power of x. It doesn't matter to me what it is. We just want the setup. You can write to me something like this in the notes, guys, in the comments. You can write something like outer S, and then you say S, big S, then you write number, and then an inner S, number, and then you write d something, you know, maybe dy, dx, or, you know, dx, dy. You understand? So you can write in the comments this way to tell me what should I do. Thank you, Sarah. And for the other direction? Okay, just look at it carefully. Sarah, you should think which comes first and which is last, right? So I think what is x from 0 when integrated for just an arbitrary y. All right. I wait 2 more minutes, guys. Let's see it here, guys. So let's first do the red description. So here, if I move over here, I integrate the function f(x,y) with respect to y. Agreed? So what is this point? Obviously, it's a line, so this line is y equal to x. Do you agree? So this is the integral dy, integral from 0 to 2x. And then the outer integral is x varies from 0 to 1. We are done. Do you agree? If you don't understand something, you let me know, right? Because it took a while. Let me know if something bothers you. You see what we are doing, guys? We're slicing it up. What's the idea? What's an integral? An integral is nothing more than a sum, right? But that's why you have this this curvy s sign. It just basically means sum the whatever values you're adding up. So why are we summing it? So this here, guys, represents the cross-sectional area of a very thin slice, so thin that it's essentially along that red dotted line, right? It's so thin that it's essentially along the red dotted line. To make it into a volume, I multiply it by dx, right? Dx is the thickness here. This thickness is dx. And then I add over all the x's. So I add over all such red lines, and I will get the full cake. You agree? Now, if I were to slice along the green line, and there you have to look at it, guys. First is this is the small x, and this is the large x. So if I do that with respect to the green line, then the inner integral is from here. What is this? This is y equals to 2x. So that means x equals to y over 2. So that would be from y over 2 all the way to x equal to 1. It's this region of the function, dx, and then y goes from 0 to 2. So both are valid descriptions for the volume of the cake. I just made different slices. Good? Now, last part. Last part is change of variables, right? At least the very basic ones. So imagine that, for instance, I have, this is my baking pan. It's circular, right? Or something easily described in a circle. Now, this is not, I mean, I could potentially cut it into two parts. Let's say maybe if it's a circle of radius, if it's a circle of, let's say, radius 5, right? If it's a circle of radius 5, I can set the integral equal, if this is my baking pan, I can say that x varies from, let's say, -5 to 5, and for each x, the vertical value, right, for each x, the vertical part is from -√25 minus x squared all the way to √25 minus x squared. Yes, I could have done that. fx y dy dx. But this is already very ugly, and much nicer to use a different process. Okay, not to slice it like this, but to try to find a volume by trying to understand by using polar, precisely, right? By using polar coordinates. Now, what's the idea of polar coordinates, guys? Is that we're going to slice it like this, right? We're going to slice it like this. You agree? And of course, you have many. Looks like basically we're using a cobweb to create the slices. And now I need to understand, exactly, I need to understand how to find this region, how to describe the area. It's basically the function, the altitude. If this block is very short, it will be the area of that block times the altitude. Do you agree? Again, guys, my goal is not to cut this cake, but to find what's the volume of that cake. You agree? So if I cut it into many, if I use a very fine spider web, then each segment is a block, more or less. It would look like a rectangular block. Here is how a typical segment looks like, guys. A typical segment extending from 0 looks like this. And I need to know its area times the altitude of the function, because the function is continuous. If this block is very short, essentially any point within that block has the same altitude. Are you following me? The altitude, and if this section is very close, because the z is equal to f of xy, all the possible values of z are essentially identical. So all I need to do is figure out the area of that block and multiply it by the altitude. Now, what's the area of that block in polar coordinates? Well, let's see. The area of that block in polar coordinates, guys, if this is r, and this here is theta. If this is r and theta, so what is this? This is dr, and this thing is d theta. This thing is d theta. So that's d theta, and that's dr. Yes. So what d theta is? Just measuring an angle, guys. You remember what are polar coordinates? Do you still remember? Polar coordinates are just the measure of the arc in terms of radius units. So to translate it to length, what do I need to do? I need to multiply it by r. You see? For the same angle, I make r longer and theta gets longer, right? So this is just an arc of a circle. So I don't need the theta, I need the s part. I need the s part, right? So I know that s divided by r is equal to d theta. So that means s is equal to r times d theta, which means because it's roughly rectangular, if d theta is very small, it's roughly rectangular, so the area is simply r d theta dr, or better, you can write it any way you like, right? Either r dr d theta, whatever you like. That's the area. That's why we multiply by the corrective factor, and we add up over all possible r's and all possible thetas. Yes, so that means that this integral can be written as, in this case, r is from 0 to 5, theta is from 0 to 2 pi. The function where I change the coordinates in terms of x is r cosine, r sine, because what is x? X is r cosine and y is r sine. And then you multiply by in this case, well, I would like to put it as r d theta dr. Are you with me? Do you see why we have this double integral? It's a matter of summing, guys. What am I doing? I'm summing over all the possible thetas over all the possible r's. If you understand that double integration or any integration is nothing different from a sum, they become very easy, and formulas, many of them are very easy to extract. Do you now understand the change of variables for this particular case? Jack, what bothers you? Okay. Yeah, I know it's okay. I mean, the ship has sunk anyhow. Yes, so think about the geometry, guys, and what do? We add up over theta 1, theta 2, theta 3. We add over all the, in this case, over all the, first over all the thetas, right? So for each particular r, here is a particular r. We add up over all the thetas. You see, this integral is expressing, the integral, the way I set it up, is expressing the summation this way. So I go like this, like this, like this, like this for any particular, and then like this. You understand? So the way I set the integral up, I mean, for any fixed r, I find the sum of all the blocks. And then for the next r, I find the sum of all the blocks. You understand? And if I change coordinates, what happens? If I change coordinates and I make r the inner angle, then I would find it like this, right? So this is one way to find it. If I reverse the integration and angle is outside, then I add the same thing up, but then like this. So for a fixed theta. Agreed? Okay, guys, so why is it so simple? Because all it is just summation. How you have been doing summation all your life. And now back to this miserable integral. Let's just at least kill it. So this is what we verify, guys. I want to know what's the integral from just the single integral from minus infinity to infinity of e to the minus z squared over 2 dz. Now this is the same as the integral from minus infinity to infinity of e to the minus x squared over 2 dx, or the same using y. If I square I can multiply the expression with x and with y, and then I realize I am getting this. It's just like I'm multiplying one summation by another summation, and I will get summation of every combination. Yes? I will get this expression, guys. Good? It's just a sum, right? If you take the limit, it just when I think of continuous random variables, I truly always think discrete with lots of very close values. It's like when you think of a movie that is continuous action, you can actually imagine lots of frames, very high refresh rate, very high frame rate. Yes? So that's what we have over here. Summation times summation, it's all possible combinations, all possible sums. And what is this expression? Oh, I realize it's an infinite circle. You agree? Because it's the entire R plane is like an infinite circle. So I'm going to describe an infinite circle like this. So it has infinite radius. So the radius is from 0 to infinity. Angle is from 0 to 2 pi. And here is my function. Replace x by r cosine and y by r sine, and you have this. And r d theta, that's just corrective factor. Right? The r d theta is the area of a small box, or a small frying pan, as I drew in this cobweb. And this integral is now easy to calculate. It's just a basic u substitution. I can first of all separate the d theta, 0 to 2 pi d theta. I can factor it out and solve it separately, and I can solve the remaining integral with just r separately. Yes? With respect to theta, I can factor this, this inner number. You see that what I do is I take this number, I take this, and I move it outside the integral sign. It's just a constant. Yes? And then I get this integral times this integral. Now this is just 2 pi. And what is this integral? This integral happens to be equal to 1. Right? Just integrate it e to the minus r squared over 2 with a minus in front of it. So that just happens to equal to 1. So the result is 2 pi. So I squared is 2 pi, which means I is root of 2 pi. So that explains that coefficient. Normal distributions are not easy to understand at all. And then we go through the description of the normal distribution. I suppose in the last 3 minutes, unless guys, you really want to stay with me another 5 hours, I suppose we reached our limit. So I apologize deeply that we haven't finished all the lectures. I hope you're not going to be limping. You know, you have the notes. If you're bothered by something and want my explanation, you know, maybe over the summer. So I wish you very good luck on the exam. Again, to reiterate, you see, I haven't taken any action just yet, but I'm well aware that some people did not listen to what I said. Please don't do that for the final exam. I do not want to injure you. I tend to, for this class, tend to not fail people because I figure probability, you know, they are interested and motivated enough for the subject to self-correct, right? Unlike, let's say, calculus students who are just inflating the education system to make it just air. So I don't bother you as much. But if I see that it repeats, I will get upset. And if I get upset enough, and I decide to devote my time to it, I will fail anybody who I catch cheating. In other words, there is one phrase, one sentence, something posted online, something I find out, I will fail you. What for, guys? You don't need to get 100 on this exam. You don't need to answer every question. Enjoy it. Try to answer them as good as you can. The grades are, you have 100 for the second exam. This first exam is, you know, I think you probably did pretty well. What's there to worry about, right? Just don't overextend yourself. Good? We agree? I know most of you do, guys, but not all of you. I hope that those that did not agree last time, they will agree this time. Good? All right, guys, if you want what, when, where, we can play 1 or 2 games. And if not, and if you're tired of me, I wish you the best of luck on the exam. Please submit it by May 25th because I have to post a grade very soon after. And if you have questions about the final that you need clarification, we can address that right away. Do you want me to first clarify what you have for exam? Anything I can help you with? Anything that bothers you?
Can I ask a question about the first question?
Yes.
Are the spaces counted as letters?
Yeah, I'm sorry. A lot of people ask me that. No, they are not. And if you interpret it as counting, I would still give you the full grade, right? So the spaces are not counting. I just, yes, I wrote it with spaces to help you read it. But if you want to, you can count spaces, you see. I think don't bother. Good? Great, guys, spaces are not, they don't need to be counted. Good? What else?
For question 6, like for the so for the red point, so like are we calculating like the length of the whole segment containing the red point?
Sorry, because of the microphone a bit muffled, I did not fully process.
Okay, so for question 6 about like the red point, so are we calculating like the length of the whole segment?
Yeah, the length of the whole segment.
So like, are we assuming, for example, like there's like, so when like this is cut like into 2 segments, like one of the segment contains the red point and the other segment doesn't contain it, so.
Just the segment that contains the red point, the full length.
Yeah, I mean like, so are we assuming like when we cut like one of the segment contains the red point and like the other one doesn't contain.
Yes, because if it's truly a point, you will never actually cut it at the point. The probability of cutting it at the point is 0. Yes, so I mean, you are thinking of an actual point, which can be a big circle, or you can break it into 2, right? But a true point has no breadth. It's it has no, it's a 0-dimensional object, right? So you cannot cut it. You can also not get at it because of probability, right? But probability of cutting at a particular point, if it's a continuous random variable, is 0. Good? Question 10, of course. No, what's question 10? Remind me.
It's falling off an air conditioner.
Sorry? The air conditioner, yes. Yes, yes, what about it?
So actually, your hints kind of confused me.
My hint?
Yeah.
Oh, good. So don't pass by my window, then you'll be okay. Yes, just you can ignore that hint if you don't like it. So just I don't know what the actual statistics. I was just wondering what's the actual statistics of somebody being hit by an air conditioner falling from the window. But imagine it's not very frequent, right? So I just decided it's once every 5 years that somebody is injured as a result of that. Okay. So the question is, what's the probability that somebody will be injured? So one person every 5 years is injured by a falling air conditioner. What's the probability that this year nobody will be injured? Good. Make sense, guys? You can think about which distribution is best to use here, right? You have many people, many opportunities, and very little chance of success. Yeah, so you should be right away aware what to do there with this question. Good. Anything else? Fall, yes, let's do that. Fall 2020 exam problem. Why not? Let's do one. It's which exam? Is it exam 2? Yes, I'm listening. Which question? First? Oh. $11. All right, 11 is, how do you say, it's a bit difficult. It's extra credit. So, well, let's see how, so what you have is, you have the frog and the snake, and the frog moves randomly. Yes, back and forth randomly. And the probability, not quite randomly actually, right? The probability that the frog will leap to from k minus 1 to k will be k over 10. So for example, here, the probability that it would leap to 2 is the probability to go here, it's the probability it would go to here is 1 over 10, and therefore 9 over 10 that it will move to the right. See, so if the frog is in position 1, it will leap to its death with probability 1 out of 10, and to survive, to place 2, 2 out of 10. Yes, I mean 9 out of 10. I'm sorry. Good. So it makes sense, guys. So for any position that the probability it jumps back is just the position where it's located divided by 10, and the probability it will jump forward is 1 minus that. Great. So make sense? And the question is, find the probability that the frog survives. So what you can do is you can in some sense you can condition, right? So you can say, you might define maybe probability given that the frog K is probability of survival from position K. And we want P1, agreed? Which I'll just label as P. You agree? So, what's the situation then? So I can see that, for instance, we can decide based on where you jump. So basically probability, we can in general have this probability that you survive at K that will be weighted based on where you jump. Do you move to the left or do you move to the right? So it would be K times 10 times the probability K minus 1 plus 10 minus K over 10 probability K plus 1. Do you agree? So that's the probability of survival in K. I can just break it and relate it in terms of K minus 1 and K. And by the way, I do know what's the probability at 5, right? So if I'm at 5, then it's 5 and 5 over 10 and 5 over 10. So over here, survival by symmetry will be 1/2. Right? I do know, for instance, right away that probability at 5 is 1/2. So far good? All right, let's see. Let me actually write it on a separate sheet. Right, so then we already defined all symbols. Probability of 5 is 1/2. And I know probability, I need probability of 1, given if I'm in position 1. And I know that in general probability of at K is K divided by 10, probability K minus 1, plus 10 minus K over 10, probability of K plus 1. So and I can also possibly use even more symmetry. Do you agree that probability of survival is if you move onwards, it's like I just need to really work with probabilities. So for instance, if I have a probability of 6, probability of 6 is probability to survive if I'm in position 6 is by symmetry, if I'm not mistaken, 1 minus the probability that I survive if I'm in position 4. Am I right? Because basically by symmetry to survive into position to move onwards to survival becomes the same as dying from 4. 1 minus P4 is dying. You see what I mean by symmetry, right? So there is symmetry there as well. Yes? You should, guys, if you think enough about survival and death, then of course you understand that to survive and to die, it's very symmetric. Yes? So to go to the snake or to go and go to the other safety, it's very similar, right? So definitely very similar beyond 5. Good? So what can we do? Then we can begin with P of 5, right? So P of 5 is, and so P of 5 is on one sense, it's 1/2. So we have 1/2 is P of 5. And by this property, it's equal to 1/2. It's another 5/1/2 P of 4 plus 1/2 P of 6. Yes? You see that? And what is P of 6? It's what we now have is that from this equation we see that 1 is equal to P of 4 plus I don't want to cancel it, so that's P of 6. 1 second, guys. Maybe I'll begin with P of 1 simply, right? So P of 1 is going to be it's going to be the 9 divided by 10 P of 2. Yes, and that would be 9/10. P of 2 is P of 2 is then what? P of 2 is 2/10 P of 1 plus 8/10 P of 3. Yes, and so let me actually even you can then move. You can see that we with this information we see P of 1. I can move P of 1 and solve in terms of P of 3. But maybe I'll just write it this way, right? So guys, just a second. So P of 1 is 1, or it's P of 1. I only can jump to the right, so that would be 9/10 P of 2. Now P of 2 is P of 2 is 2/10 P of 1 plus 8/10 P of 3. And then I go with P of 3. P of 3 is 3/10 P of 2 plus 7/10 P of 4. Yes, and then P of 4 is P of 4 is 4/10 P of 3 plus 6/10 P of 5, which is then simply equal to 4/10 P of 3 plus P of 5 is 1/2, so it would be plus 3/10. Yes? So we have a lot of those equations. So you see what we can do. We can replace, we can just replace P of 4 in here, right? And then we can replace, you see, we can just using those equations, we can cascade all the way down to P of 1. It's just a matter of algebra now. You agree? You might find a quicker way to solve it, but essentially you can do it this way. For instance, that's how I figured it out, more or less, right? So because you see, I now have P of 4 in terms of P of 3. I then have the equation. You see, I can replace this. You see, here's P of 3. I can put it back into here. You see, it's basically like this, right? So here I have P of 4 in terms of 3. And then here I have P of 3, and then here I have P of 3. I then can figure out P of 2. And right, I can figure out P of 2. Here I put in P of 3, and I have it. right? I have P of 2 and P of 2. I set it up. I can go back. Good? Yeah, all right. Anything else? Ah, the games give the same benefit. Okay, interesting. That's a good question, guys. So you either have 5, 6 or 6, 6. Which would you prefer? Or there is no difference? All right, guys. Well, I kind of don't want to steal the pleasure of your trying to understand this question. But what do you think? Is there any difference or not? Maybe there's no difference. It's equally likely. It doesn't matter which game you play. So you just need to figure out which is the better game, and of course not to just guess, but you have to calculate the expected value for each game. Let's do it this way, guys. Right? So I would let this problem rest with you. Maybe closer to the end of the semester, we can discuss it if you want to. If you just message me and we will schedule like a party. Very safe, sterile party, as we have been scheduling for the past 2 years, or 1 year, I don't remember, and then we can answer this beautiful question. Yes, the person that I owe the pleasure to know this question was my former student. He was struggling with it, asked me how to solve it. I solved it for him. And I said, so why aren't you visiting me in person? He said he's afraid of Corona, right? So he's asking me probability questions, but he's afraid of COVID to visit. Poor old Arkady. When it all started, did I tell you I had office hours in the cemetery? Right, so guys, let's play a what, when, where. What do you think? And if you really like this question, think about it. I think it's interesting. It's a very interesting question. And then we can discuss it once you had your fun with it. Good. So I'm going to play a what, when, where with you guys if you want.